it's 17 past, so I'm allowed to start. So today, if you watched the last Quinbox, we're going to take a whole bunch of different wire sizes. Actually, let me show you on this camera. So lots of different wire sizes, and we're going to run actual LED current. This is now a thing called LED current through them to see what the effect actually is of not using the proper wire gauge. So we have like 24 gauge or we have like 8 gauge. Does it make a difference? Will this instantly go up in smoke and flames? Well, I got my I did prepare some stuff, because I have my my can of fire stop here. So if there's a fire, I should be able to stop it. But let's hope I can stop it before it becomes a fire just in the smoke stage. I guess I could unwrap these wires now. I did get my silicone mat out to see if that'll stop a fire. Anyway, fork terminals. Don't have more of these. These are all I have. But I do have a lot of a lot of fork terminals, and I'm guessing those would actually work just fine. Right. So okay, we can do that. I'm generating the 40 amp load with 6 5-volt LED bars, and this is also a 5-volt power supply. This is the UHP-500-5, which is not 5-volt. There we go. So this is the UHP-500-5, and it takes 4.7 amps in at 230 volts, and then 80 amps out at 5 volts. I mean, yes, I have my CCA tester right here. So yeah, we're going to be testing if it's copper or CCA, using flames, which is always a good idea on a live stream. Yeah, exactly. So 8 gauge was just like, oh, they have 8 gauge on the list and it's not too expensive. Okay, let's get it. Maybe not. So at least on the AC side, we'll have a good connection. Yeah, 24 gauge is also on the list, and that is either 24 or 26 is often used in Ethernet cabling. But Ethernet cabling isn't suited for a lot of power. PoE works because it's a very high voltage. But even then, I don't believe they use more than half an amp or something like that. I use both AWG and millimeter squared. I'm a Dutch guy, so millimeter squared is actually the thing over here. But talking online, wire gauge is often pretty easy to use also. I did put a calculator in the description with which you can convert. So all these cables are in gauge, and then you can just input like, okay, 18 gauge, and that is like 0.8 millimeter square and stuff like that. Right, so these AC connections should work. Conclusion of 8 gauge is it's too thick. Don't use it. Okay, great conclusion there. Let's see what we have then. Then we have 10 gauge. And 10 gauge, it doesn't actually say what the millimeter square is. 10 gauge is 5.2 millimeter square. That's really thick cable there. And let's see if we can get that into these terminals, because I think, or into these fork connectors, because I think those would also fit on the board. Yes, perfect. And we already tested it on here. So, first problem with large gauges, how do you even hook it up? And I thought I had a lot of fork and ring connectors, but it turns out those were spade connectors and not ring. I didn't think getting the cable to fit into the terminal would be this big of an issue. Yeah, so 10 gauge, we're going to sideline 10 gauge too. There we go. I guess we'll start with, what do we have here? 12. 12 is 3.3 millimeters square, so that should fit into this ferrule. Or actually into the blue spade. The blue fork. Yeah, sure. That'll work. I can crimp that. I keep stripping off too much. But for this test, I'll take it. Right? Yeah, that's fine. I mean, this is not a good crimp or cable connection, but it'll do for the test. No, you can't, with this type of power supplies, you cannot use the bare terminals, or the bare wires into the terminals. That'll never work. Second thing to decide, now that we have a cable we can actually mount, is how long are we going to make our testing leads? Because we want to keep the length the same, and we're going to be testing basically the input into a Dig-Quad. And a prototype model with bigger terminals, but sure. I'm thinking something like this, right? And then we'll just make all the cables the same length. Because that is this centimeters? Oh wow, I actually have a centimeter scale on here. So this is, let's make it about 50 centimeters. This is from the power supply to the Dig-Quad. So I think 50 centimeters is a reasonable value. So let's adjust my crimper to not make stupid long crimps, or cable cutter. Cable stripper. Cable stripper, yes. Yes, that's much better. Yes, see, that's much better, because now they basically fit together without any exposed copper. Which is what you want. Perfect. Okay, so these are now securely crimped on there. So that's good. Let's do a CCA test real quick. Is by burning it basically. And if it's copper, it should get red hot and not break off. But if it's copper clad aluminium, it should start curling back pretty quickly and then start breaking off and actually almost dissolving. Because, well, that's just different properties. So let's see what happens. It's looking pretty good. It should discolor a little bit if it's copper, turn kind of blackish. This is getting pretty warm in my hand. That sucks. But yeah, this is copper, because copper-clad aluminium, I've seen it before, just starts to break down, basically. Let me get we can torch it some more. But you see that it's glowing red hot, and it's not really breaking down. No, you don't need to use one strand. Yeah, I've seen CCA before, and CCA, I don't have CCA to demo, no. It's a nice bit of smoke here. But I've seen CCA before, and that would have definitely already started peeling back and breaking down, and yeah. Okay, so now I have this smoking hot piece of copper here. Well, we have a silicone mat. It should hold. That's fine. There we go. Let's put it there. Okay. So, first we want to know is what voltage is the power supply currently putting out. And as you can see, that's a very nice 5.09, so let's say that's 5.1 volt. Now, the tests we're going to do is, by using a cable of this length, what voltage arrives at the board? Yeah, this 200 watt LED sun. So if we're measuring here, we see that we only have 4.8 volts reaching the board. That actually means that this cable is already... Oh, it's already getting warm, actually. Wow. But because it's getting warm, that also means that it's dropping voltage because it's losing energy, which is being transferred into heat. And this cable has easily gotten 10 degrees above ambient. So, as I said, we had 5.09 coming in. Exactly. But then at the board, we only have 4.831. So that means we've lost like 0.2 volts somewhere. And, well, that is lost in heat. And that also already shows you how important it is to use the proper wire gauges, because if you use, well, we're going to do that soon, smaller gauges, well, this will only get worse. Right? Oh yeah, these cables are rated for 200C because they're all silicone. Oh, wow. Wow, it's hot, it's warm. So let me get out the Flir. Can you guess which fuse is running 2 bars instead of 1? So this fuse is currently 84 degrees. So here the cable is a single part, that's 52. And then over here it's actually getting quite hot. The cable is already 60 degrees. Now this is silicone cable, so that's fine for that. That can go up to 200 degrees basically. Yeah, it's hot. It's definitely hot to the touch. Because I want to do a test, because we can already see that this cable, which is 12 gauge, which is nuts. Let's turn this off. Is already getting quite hot. But what if you actually do want to run this amount of power through the board? Well, you double up cables. Right, okay, we have the orange display again. And I'm not going to show you double LED because we're just going to go to white. We're at 106 watts and we go full power. And we're at 204.3, exactly the same as we were before. But now let's see what the voltage is. Because I expect on our power supply over here, 5.09. 91, okay. 5.09, that's really tightly regulated, 5.09. Okay, so on the power supply side, we're seeing exactly the same as we had before. But now let's see on the board side, 4.967. So we're losing from 5.09 to, well, 4.96. So we're losing less than 0.1 volt. I mean, we can check the other terminals and combinations and stuff like that. Yeah. So we've improved the voltage drop going from the power supply to the board. So now the board gets a higher voltage because there's less resistance on the cables. So less power is being converted to heat. Yeah, that's way better than before. Yeah, absolutely. And I mean, this wasn't some cheap-ass cable. I mean, I can actually now measure on the cable. Yeah, that's fine too. So that the terminals don't add too much resistance either. And we can actually also measure the other side. So going through the board, of course, there's also going to be resistance. But even this being 1 OZ, because of the power planes and stuff I have in there, we're going from 4.96 to 4.85. So that's less, that's slightly more than 0.1 volt drop. But anything transferring power will have power loss. And this being 1 OZ instead of 2 OZ, that's actually not too bad. Right, so cables, 37. My fingers, where are they? 37.6. Anyway, let's see the board connection here, because that should also cool down now. They're about 43, 45. Let's see over here. Nope. 41. 42. Yeah, when there's something hot here, so the fuse is actually running hotter than before. It's almost 90 degrees now. But that's probably because the voltage that's going through there is now higher, so there's likely more dissipation. But yeah, 40-degree cables are perfectly fine. 203.5 watts. And let's... Oh, I was going to say let's give it a little bit, but these cables are already getting warm. Damn. Okay, sure. So, power supply should be 5.09. Yes, 5092, 5091. This is a very tightly regulated power supply. Okay, and on the board we're seeing 4.774. So 2 times 16 is slightly worse than 1 times 12. But because now we've dropped down in wire gauge, if we're running 40 amps, the output of the board is only 4.65 volt. And of course, if we say, okay, let's do half brightness white, well, you can see that now the cables are adequate for like 20 amps or something like that. But for 40 amps, well, you can see the effect, basically. If we go to 1/3 brightness, let's do that. There we go. So this is 60 watts, 4.978 volts through the board and the cables and everything. That's fine. 2/3, so now we're at 140 watts, 4.8 volts. That's okay-ish. But then going to 200 watts, so 40 amps, 4.65 volts, that's a bit low, because then it still has to go to the LEDs. And then it'll drop even more, so by the time it reaches the LEDs, it's going to be like 4.5, 4.4 volts. So you can also do these tests in your own setup, measuring from the power supply to the board, how much you're dropping there, and then from through the board, and then through the board to the LEDs, and you can even figure out that way if you spec your cables correctly or not. Wow, ow, these are getting hot. Okay, let's see how warm they're getting. It's not too bad. It's, let's see here, 47, oh, 54, 53, 50 degrees. You can actually see on the Flir like this that the cable is much hotter than my hand now. So these are 55, 53. Yeah, 202 watts. Okay. Can the Flir handle 200 degrees? Don't know. No, Rupert, you're still in time. We're now doing 1 times 16 gauge for 40 amps. So this is still 509. Oh, okay, air cookie. We're now doing a single cable instead of the double ground, and we've dropped down to 4.3 volts instead of the 4.5 we saw before. So the double ground did seem to do something. Wow, okay, 4.3 volts. That's already dangerously close to the board shutting down. Now, it isn't shut down because it needs 4.5 volts to start. But once the board is running, in my testing, it'll stay running down to 4.2-ish volts, something like that. But yeah, this is getting dangerously close. 4.18 volt output to the LEDs. Okay, let's see. Oh, wow. So the Flir doesn't actually know, and it's saying about 128 degrees. So can you see that? 134 degrees. That is not okay. 140 degrees. And this is 16 gauge cable. If this would have been PVC, this would have been melting all over the place. I mean, you can see... Oh, okay, you can't see how floppy it's gotten, but... 130 degrees. Red, red, black, black. Yeah, looks good. Okay, so it turns on. We're drawing 34 watts with the standard orange pattern. The power supply is giving us 4.098. That's a little bit higher, but still very accurate. And the board is reading 4.844 while we're only doing 34 watts. Oh no. Okay, so what I think will happen, let's see. We're now at half orange. Let me go to full orange. So we're now at 60 watts going into the power supply. Yeah, this cable's just... I mean, the cable going to the LEDs is thicker than to the board. But anyway, we're now doing 60 watts. That's full orange. That's doing 4.6 volts. And so what I think will happen, if I dim that down and I go to white, and let's go to half white. Yes, 103 watts going into the board, but we're now at 4.1 volt. So that's at 100 watts or 20 amps. And this cable is rapidly getting hot. But the problem is, if I push it further... Oh, nothing happens. Connection to the light failed. Okay. Okay, it already happened. Basically, I can't control the board anymore. Because, well, we lost the signal. That's very correct. But we lost it at 100 watts. So, 20 amps. Oh, voltage is still going down. That means the cable's heating up. Yeah. We're at 4 volt. We've dropped a whole volt over that little cable there. Oh, that did it. We're now at 155 watts going into the power supply. Instead of 100. So power supply still doesn't care. 5.096, sure. Board is like... We almost don't need the buck regulator anymore to get 3.3 volts. We could run the ESP directly off of this. Uh-oh. Oh. Can you see it? There's smoke. There's definitely smoke. 155 watts. Okay, let's go. 155 watts at 5 volts, so that's like 30 amps through a 20 gauge cable. Maybe I can turn these away a little bit. Okay, no smoke yet. We're at 140 watts. Yeah, okay, it's starting to smoke. See it? Do you see it? Can you see the smoke? There's definitely smoke here. Yeah, smoking, yes. Smoking achieved. I don't want to see too much smoke. Okay, let's turn it off. Okay, but does this count as magic smoke? Is silicone smoke, like, bad? Okay, so a very short 24 gauge. Sure, that's a good test. In theory, the shorter it is, the less resistance it should have. Let's see, is this the 24? Yes, 24 gauge, okay. So then, realistically, something like that, right? That's it. Incoming voltage, still perfectly fine. We're with 34 watts in, so all orange. We're already at 4.7 volts. Let's do full orange. That's 60 watts. We're at 4.5 volts. And now let's do full white. Oh wow, it's drawing 160 watts. Oh, it's drawing 147 watts, 142 watts, 135 watts. Oh, it's already smoking. It's smoking. Let me try and show you guys. Yeah, okay. Yeah, no, cancel. Oh, God. Yeah. It's still smoking. Yeah. 24 gauge? No. Oh, man. That was releasing a lot of smoke. Well, there's coughing here. Okay, yes. No. Short 24 gauge cable? No. It started at 165 watts, and by the point I turned it off, it was at 120 watts. Because the voltage drop was just so insane much that, you know, it started drawing less from the power supply, so... Yeah, so this is the power collection, the power LED setup talk, the power injection live stream, and there is a document also. You can download that from here. That will run through several setups and show you what you're going to be, what you'll learn how to calculate, so you can design your own setup basically. And that'll take into account maximum amount of power a single injection point will take, cable length, and then copper thickness you need and stuff like that. So, we certainly had smoke, but that was expected. I didn't expect the setup to actually need 12 gauge cable. I designed it for 50 amps. I've tested everything for 50 amps. The terminals will do 50 amps, but I don't like putting things out at their maximum rating, so 30 amps it continue as it is. And that's already a whole lot. During any normal LED situation, you're not going to be using 30 amps unless you have thousands and thousands of LEDs connected to a single board with more than these terminals, even dividing it behind those terminals into more blocks and splitting it off. And you'd have to build such an elaborate setup to try and push more through there with normal LED scenarios. So, what did everyone think? Because we're running towards the end of the live stream. What did everyone think? Did you expect to see smoke? Do you understand why we saw smoke? Does this make it easier to understand why you need certain cable thickness or gauge for a certain amount of amps? And again, we were testing with 40 amps. That's even 10 amps above the board rating. Board did fine, okay. But let's say a normal scenario, you can easily reach 20 amps. So hooking up like 1 times 16 gauge wasn't enough for 20 amps. Hooking up 2 times 16 gauge was. But then again, these cables are pretty short. The longer you make your cable, the thicker it needs to be. So maybe if your power supply is not like 50 centimeters away like we had here, but it's like 2 or 3 meters away for whatever reason, you might still need to step up to even thicker cables. That's kind of the conclusion today. Calculate the cables you need. Yes, high amps and tiny wires makes heat. That's the exact right conclusion, Mako.